When scaling AI infrastructure, the instinct is to procure maximum theoretical throughput. We chase peak flops, higher bandwidth links, and faster storage writes. But installed peak capacity does not dictate the economics of modern AI. The governing metric is goodput, the actual volume of accepted, useful work completed, whether that means processed tokens, completed training steps, or validated agent decisions. This creates an engineering paradox. We build highly optimized local controllers for individual components, yet the end-to-end system frequently stalls. These local controllers are entirely rational within their specific domains. A compute scheduler allocates GPUs based on resource quotas and health. A network switch aggressively clears flow queues. A storage manager prioritizes I/O. But they share no predictive system objective. Because they operate blindly to one another, a high-throughput storage tier might initiate a massive, perfectly scheduled data read. That traffic creates a network intast, filling switch buffers, which immediately starves the remote compute cluster waiting on parameter updates. Optimizing the fastest component locally can actively create bottlenecks globally. In a synchronized AI factory, isolated efficiency often translates to system-wide failure. AI infrastructure is a single, coupled control system. Compute requires the on-time arrival of network parameters. Storage must absorb synchronized bursts, like massive checkpoints, without starving data loaders. Finally, security is a constraint. One unauthorized agent tool call or cryptographic failure halts the entire computational workflow. The conclusion is a strict barrier property. End-to-end completion, cost, and operational risk are dominated entirely by the slowest or least trusted dependency in the network. During a synchronized training iteration, compute, data, network, and storage run in parallel toward a hard synchronization barrier. Progress stops until the last dependency resolves. If a network rank straggles or GPUs pause for a massive checkpoint, the entire barrier timeline extends, leaving compute stranded. The economic consequence is severe. Stranded accelerators waiting on slow data loaders or congested checkpoint paths incur massive hourly costs without producing one accepted token. Traditional network monitoring relies on average link utilization, which completely fails to capture these millisecond-scale microbursts and tail latency bottlenecks. Averages look healthy while the synchronized job starves. Resolving this requires cross-domain prediction. The infrastructure must forecast these synchronized collisions before they happen, rather than dropping packets and applying congestion controls after the buffers are already full. Physical performance bottlenecks are only half of the coupled system problem. As AI moves from generating content to executing tasks, autonomous agents introduce a new vector of operational risk that traditional controls cannot see. A standard identity system verifies that an agent possesses a valid credential. It cannot tell if that agent has suffered a prompt injection, hijacking its execution sequence to perform a sensitive read, followed by an unauthorized external shell command. Identifying this hijacked sequence requires detecting a structural anomaly, often called a detopo defect. It means recognizing an impermissible relationship or trajectory without needing to decrypt the traffic or inspect the natural language payload. This logic requires a graduated, evidence-based containment strategy. This state machine maps the escalation path from baseline observation up through quarantine. A structural anomaly is not immediate proof of compromise. The system escalates its response only when it receives corroborated structural evidence across multiple domains. This structural coordination extends to cryptographic security. Migrating to post-quantum cryptography requires coordinating larger key sizes with network MTU limits, hardware security module queues, and routing topology. Dropping new algorithms blindly into an uncoordinated network breaks the application. For both autonomous agents and cryptographic rollouts, security is an infrastructure coordination problem. Operating an isolated security policy is dangerous. The engineering challenge is clear. Optimizing compute, network, storage, and security requires a joint view. But building a monolithic centralized controller introduces fatal forwarding latency and an unacceptable single point of failure. The Predictive Tensor Control Plane uses a 2-timescale architecture. The cognitive slow path ingests multimodal telemetry to model joint state and forecast tail risks. It publishes signed, expiring policy bundles down to the reflex fast path, which operates deterministically directly on the hardware. The fast path enforces a hard safety predicate. It verifies the signature and scope of the advice against local hardware budgets. It has the absolute authority to reject unsafe advice, execute only pre-approved templates, and automatically roll back if conditions degrade. If the slow path controller is compromised or loses connection, the cluster does not fail. The fast path allows the predictive bundles to expire and seamlessly reverts to native hardware routing and local invariants. The PTCP overlay resolves the cross-domain problem because its predictive reasoning is kept strictly subordinate to deterministic localized safety rules. Because PTCP is an overlay, not a rip and replace of mature infrastructure, it does not assume trust. It earns production authority through a strict 4-stage progression. In shadow mode, the system only observes. It reconstructs system state to prove its multi-domain forecasts actually yield measurable value over simple reactive hardware thresholds. It progresses through advisory readouts to a bounded pilot. Here, actions are restricted by strict blast radius caps, human approval requirements, and automatic post-condition rollbacks. Advancing to full production requires passing hard, measurable exit gates. The controller must prove it increases job goodput, reduces GPU idle at barrier time, and maintains unaffected service levels without increasing false containment. Performance and security claims demand continuous validation against strong native baselines. Production is an ongoing state of rigorous assurance, not a one-time approval toggle. As models continue to scale, the physical limit of AI infrastructure is no longer the isolated speed of a single switch or processor. The limit is the strict coordination of synchronized multi-domain constraints. Averages and local optimizations obscure the critical path. Achieving peak utility requires translating fragmented telemetry into structural, policy-bounded action long before a global bottleneck forms. In the token economy, raw speed yields zero return if the architecture cannot coordinate its dependencies. The required layer for modern infrastructure is predictive control.